In this example, we want to solve a logarithmic equation. We have the log base 3 of 2x plus 5 is equal to 1 minus log base 3 of x. So the first thing that we want to do to solve this problem is to get all the logs on one side of the equation. And so in order to do that, I'm going to add log base 3 of x to both sides. And when I simplify that, over on the left hand side I'll have both of the logs being added together, and on the right hand side I'll have 1. And basically the purpose for that is if I have the logs over on one side of the equation, I can use the rules for logarithms to combine all that into one single logarithm. So here's what I had, and what I'm going to do is use the rules of logarithms, and I've got the sum of two logarithms over there on the left hand side. So one of the rules of logarithms says if you have that, then you can rewrite that as a single log by multiplying on the inside there. So I have log base 3 of 2x plus 5 times x equals 1. So now I have what I need here. I have a single logarithm over on one side, and over on the other side I have a number. So I can use the definition of the log function to rewrite that in terms of an exponential function. So if you remember, right, it's log base 3. So what I'm going to have over on one side is the base 3, and then to the first power, the number that's over on the other side. So when I rewrite that, here's what it's going to look like. Right? So 3, that was the base of the logarithm, to the first power, the log's equal to the exponent, is equal to the what was on the inside of the logarithm function there. So if there's a place where people tend to mess up, it's in this step right here. They often forget to use the base of the logarithm over on the right hand side, that 3 to the first power. It's the base of the logarithm to the exponent part there. People will sometimes just rewrite the number 1 in that case, but you don't want to do that. You want to use the definition of the logarithm to rewrite that. And so what that does for us is it allows us to solve for x. X is now not inside the logarithm function, and so we can solve for it like we would in a regular equation. So looking at what we have here, what we have is a quadratic. If we simplify things by distributing the x over on the left hand side, we get 2x squared plus 5x, and 3 to the first power, of course, is 3. So what we have is a quadratic equation now, and to solve that, what we're going to do is subtract 3 from both sides, and that will put it in the form that we're used to seeing that as. So what we would have is 2x squared plus 5x minus 3 equals 0, and we want to check to see if that quadratic equation can be factored, and in this case it can. Right? So I'm not going to go into a lot of details about how to factor it, but we have 2x squared plus 5x minus 3, so there's only one way each of those numbers 2 and 3 can break down. 2x minus 1 and x plus 3. So if you rearrange that in the factors there, it's pretty straightforward. If you have questions on that, let me know and I'll put up some videos about factoring. Okay, so now we have the left side factored. 2x minus 1 times x plus 3 equals 0. So that means that either 2x minus 1 equals 0 or x plus 3 equals 0. And so now we have two linear equations, and we can just solve those by adding 1 over to the other side and dividing by 2 to get 1/2, and on the other one all we have to do is subtract 3 from both sides to get x equals minus 3. So what we have now are two potential solutions. One of the issues with logarithmic equations is that you could do every step perfectly and still come up with answers that are not solutions to the original equations. So to get everything perfect, you must check all of your solutions that you have. So we have two solutions here, x equals 1/2, x equals minus 3, so we'll have to check both of those. So let's start with the more difficult one, and that is x equals 1/2. So what you want to do is just go back to the original equation. So that's the original equation there, and substitute in the number that you're checking. There's the solution that you're checking. So in this case, 1/2. So I plug in 1/2 for x, and I'm just going to do a little simplifying. On the inside there, 2 times 1/2 is 1 over on the left-hand side. And then if I add, I get log base 3 of 6 equals 1 minus log base 3 of 1/2. So there's a couple ways that you could go from here. One way is to plug that into your calculator, and both sides into your calculator, and see if you come out with the same thing on each side. To do that, you would have to use the change of base formula in this case. So because your calculator probably only has log base e, the natural log, and log base 10, the common log. So this one problem is log base 3. You'd have to use the change of base formula to change it to a base that your calculator deals with. So I'm going to take a little longer approach and just kind of do it by hand. So what I'm going to do is just do like I did when I was solving. I'm going to add log base 3 of 1/2 to both sides and get all the logarithm functions over on the left-hand side. And then again, I'm going to use those properties of logs to combine the left-hand side where I have 2 logs being added together. I'm going to use the properties of logs to combine that to a single log. And again, how that works, right? If you have 2 logs being added together, the same base, the property of logs, one of the properties of logs says that you combine that into a single log by multiplying on the inside. So what I wind up with is log base 3 of 3 is equal to 1. And log base 3 of 3, right, whenever you take the log, whatever base of the base number itself, it always is equal to 1, right? What power would you raise 3 to get 3? Well, that would just be 1. So I wind up with 1 equals 1, and that checks out. So the conclusion for 1/2 is that 1/2 is a solution. When we plugged it in, simplified everything out, we wound up with a true statement. So 1/2 is a solution. All right, on to the next potential solution, which was -3. So we're going to run through the same procedure there. I'm going to go back to the original equation. Where there's an x, I'm going to plug in -3. And when we do that, there's an immediate problem that happens. And the problem is that over on the right-hand side, I have log base 3 of -3. Well, in this class, right, the logarithm functions have domain positive real numbers. So what we get is a domain error over there. -3 is not in the domain of log base 3 of x function. So therefore, -3 can't be a solution in this case. One thing you need to be a little bit careful of is that some people see an example like this and they automatically conclude that you can't ever have a negative solution to one of these logarithmic equations, but that's false. You can have one. It just depends on the equation itself and how things turn out there. So don't automatically throw out any negative solutions. The procedure is you plug in the solution and see what happens. If it does lead to a negative inside the logarithm function when you start simplifying, then you can stop. There's no point in going any further. So the final answer on this one is that the only solution of this equation is 1/2.